I appreciate the opportunity to present our work to this august audience. I'm also grateful to our collaborators and contributors to this work. So today I'll be talking about neural models for graphs, in particular in the service of searching for them, ranking them and scoring them. Graphs form a very convenient common representation between images, molecules, text passages, tables, relational data, and natural language queries which can be used to probe those data sources. For example, if you have a database of molecules and a query molecule, you can think of them as graphs with nodes being atoms with specific properties like mass and atomic number, and edges as bonds with valence and energy levels, and use this query to retrieve certain molecules which are structurally and therefore hopefully somewhat functionally similar or related to the query molecule. So the molecule is a graph where nodes are atoms and bonds are edges. If you want to do image search, an image can be analyzed today to find regions which represent objects like a horse and a man with a hat who has a face, etc. And these can be turned into a graph where the nodes are objects and the edges are spatial relations, which can also be turned into functional inferences like the man is riding the horse as against feeding the horse. And this helps us respond to keyword queries better than if we just look for a horse and a man. In fact, even if your query is an image, you can turn that into a graph and search for it in a larger database of images which have also been turned into graphs. But the question that I'm closer to is doing question answering over tables and text. So suppose your query is the birthplace of a cricketer who led the winning team in Adelaide in 2003. Now, what kind of sources can I tap to answer such questions? Here is a passage from Wikipedia, which starts from Sourav Ganguly was born in Kolkata, and then many paragraphs later, in 2003, Ganguly was captain of the Indian cricket team. Now, that still doesn't answer my question. That may come from a cricket enthusiast's website where there's a table listing matches and venues and winners and losers. But I can harness these sources to answer this question credibly only if I bring them to a common denominator representation. For example, we have techniques today that can turn this question, although it's not really a question ending with a question mark, into an incomplete graph where the unknown cricketer is E1, the unknown location where he or she was born is E2, E1 was captain of a certain unknown cricket team, but we know that the cricket team won a match in Adelaide in 2003. And we know the types of those objects that are attached with the orange colored nodes. Meanwhile, we also have techniques which can take text like this and turn them into other kinds of graphs. For example, Sourav Ganguly was born in Kolkata, Sourav Ganguly was captain of the Indian cricket team in 2003. Now, although this looks like a structured graph, the nodes may have unstructured text in it. For example, here we have Sourav Ganguly and here we have Ganguly. There are techniques which analyze and figure out that they are really the same entity and should occupy a single node. That's coreference resolution, but these are still text nodes. Finally, even from tables like this, we can construct somewhat regular grid-like graphs which tell us that there is a row in this table where the first column is called venue, which happens to be Adelaide, and connect them up like that. Now, there's still a lot of non-triviality to try to do inference on these things. For example, India and Australia here are not the nation states or their armed forces, right? This India is actually an alias for the Indian cricket team, and that's a more subtle thing to try to analyze given the context of the query and the relevant documents. After getting all these graphs, is there some magic procedure which will link up these two Gangulys, attach it to this node, figure out that this Sourav Ganguly was born in Kolkata and that locally matches this template over here, right? And Ganguly was captain of the Indian cricket team and that also fits in very nicely. I can instantiate E3 to the Indian cricket team and that this India is the same as that. So how do I do that? So that will be roughly the motivating application with which I will start an attempt toward formalizing what we want to do. Okay. So here we have a database or corpus of graphs GC. Each graph here is GC. It belongs to a large corpus of graphs. Here I have a query which is GQ. In this example, it's a triangle. Now, if I ask you which of these graphs embed naturally this triangle, we can easily see that this graph embeds it twice, this graph embeds it once, and there is no perfect fit for the other graphs shown in this sample. If I have a nice scoring mechanism like a Google search for graphs, it would score and rank these graphs so that the ones that successfully embed a triangle would float to the top and the ones that don't would sink to the bottom. So that's my goal. And I'd like to train this ranking system with some parameters theta so that this happens. I do not want to supervise the system with an actual node by node or edge by edge alignment of the triangle to the larger graph. That is too laborious. We want to supervise the system with, say, only binary relevance levels, saying that, oh, given GQ, I like this GC or I don't like that GC. Because that level of supervision is easy to obtain from click logs or from even eye tracking or gaze tracking studies of people's behavior when they see a search engine response page. That's routinely how search engines tune their ranking functions.
So, when you permute the vertices,
yes.
Are they different graphs to you or same?
Good question. So, for the moment, we are looking at the graphs as abstract objects where any node can map to any node. Gradually, we'll start informing them with, say, the nature of the keyword or its deep embedding, or if this patch looks like a horse. So that will assert better constraints and limit your search space. So let's try to go further toward a formulation. Suppose we have GQ, that triangle graph, and this GC where it does embed. And for technical reasons, we'll pad it with nodes so that the number of nodes in both the graphs are the same. And these are the adjacency matrices of these two graphs. So this means A doesn't link to A does link to B, and B does link to A, so that 0 and 1s give you the pattern of the edges or non-edges in the respective graphs. So we call this AQ and we call this AC. Suppose someone gives us a correspondence between the nodes in the two graphs. So someone suggests, it's like a magic certificate, that A maps to A and B maps to 3 and C maps to 4. Now that's not a particularly smart move because on this side the edge AB exists, but on that side the edge 1, 3 does not exist. So this is clearly a poor choice of assignment, but just to demonstrate what that does, we represent that bunch of assignments with this square permutation matrix S, showing that A goes to 1 and B goes to 3 and C matches 4, etc. Right? Given that matrix, I can compute this quantity S, AC, S transpose, which basically permutes the rows and columns to try to align the adjacency matrices of AQ and AC. Right? Now, once this happens, I can compute this central quantity. So this is AQ, that is the old AC, this is the remapped or reordered AC. Now observe that this edge exists on this side. So AB and BA exist, but in the permuted adjacency matrix, we don't have 1, 3 and 3, 1 exist. That edge is not there. And that shows up when you make a subtraction, and this plus means we take the positive sign. So if there are negative entries here, we just ignore them and pull them down to 0. So we see that there are these two 1s sticking out, and that says that this S has failed to align the triangle to the graph. So this S is actually not a best possible choice. Right? And so all we need to do to find if there's a violation or not, or how much violation there is to count the number of 1s in this function. So max of 0 and AQ minus S AC S transpose, which is the shorthand subscript with a plus. Okay. A better choice or an optimal choice would be this S, which maps A to 1 and C to 2 and B to 4, because this whole triangle then maps into a triangle. Depending on the application, we might or might not want to penalize the match for extra edges on the GC side. If you are making a search query saying, I want to find a man riding a horse, if there's a dog running alongside, you may not mind. So I will today consider the case where GC may have extra nodes and edges, and those don't bother us. That's why we take this asymmetric ReLU function to represent that the corpus having extra things doesn't bother us. The query not getting covered by the corpus rearrangement is what's bothering us. Now, so our objective now is to search for this certificate S, which will align things successfully. I want to minimize this bunch of red edges, right? There's none in the better example, there's two problematic entries here. So I want to do that. The first problem is this quadratic involvement of S, which makes computation kind of messy. We solve that by first running a graph neural network. I won't go into the details of that with only 15 minutes or so. And then we approximate the involvement of S to a linear involvement, which basically makes it a linear program of some sort. But there are no guarantees that the graph neural network will actually capture fully the semantics of the edge neighborhood of a node. The second problem is that this minimization over S as discrete permutation matrices is of course intractable, and in fact variants of graph isomorphism are some of the most notoriously difficult problems in complexity. So we are not expecting to get a magic solution to that in the worst case, but the hope is that neural networks can discover simpler regularities for real graph alignment problems and learn to match them for future graph pairs pulled from the same distribution. So we relax the space of S from the space of permutation matrices to the space of doubly stochastic matrices, or the Birkhoff polytope. And then we use another neural network to search for continuous points in that polytope. So there are two simultaneous things going on. First of all, I want to search for that certificate or a continuous relaxation of that. And I also want to tune a graph neural network which will distill AQ and AC in a form that can be matched easily. So it's two collaborating neural networks trying to solve this alignment problem. But this is also not enough. The third consideration is that the intersecting subgraph may or may not be connected. In the previous example, the intersecting subgraph turned out to be a triangle which is connected, but of course that need not always be the case. Before I get to that problem, let me demonstrate what kind of benefits such a system might have. The S that we infer is of course not 0, 1, it's a grayscale. So here are what are called two planted examples where we already know there's a subgraph isomorphism between the two graphs, and I've reordered the edges so that here is a correspondence of edges as a perfect diagonal matrix. Our algorithm may find something a bit more fuzzy. All the colors are not showing properly, but there's some level of grayness on the leading diagonal. And this tells us that some edges are so unique, like there is no other edge which has three other common neighbors, and those result in the hard matches. And then there are edges which are locally isomorphic to each other, like here are the edges at the corner of the universe, and if those are flipped with each other, local featureization will not discover that, so that smears out a bit, right? And that's okay, because all we care about really is floating the graph to the top and giving a reasonable explanation of why this graph was good, right? And here's another example where you might have something like a benzene ring, and we do this remapping, and in a real application we can color code the query graph edges and then draw fuzzy colors on the response to justify why the match happened. In the current climate of opaque and monolithic neural networks, people don't really understand when these systems make a mistake or why they get something right. At least we can surface the approximation to the S matrix as an explanation of what we are trying to do inside. Now, coming back to that problem, if you look at GQ as this couple of hub and spoke models connected by a little bridge, here is one graph, here is another graph. Which one would we prefer? Both of them miss exactly one edge. This central bridge will not map to anything useful here. There are multiple edges separating the two stars, and that's a miss. In the lower case, the middle bridge edge does map to a edge in the corpus graph, but we miss one of the corner edges, so that there's no counterpart to that. So the loss function for both would be 1 or 2 depending on how you're counting edges, but in many applications people would prefer the second graph because the match comes in one connected component, whereas in the first case the match is in two separated components. And that's something we don't like, because remember the Sourav Ganguly and Indian cricket team story. If there's some other person called Sourav Ganguly who is unrelated to cricket, we don't want to report two closely matching subgraphs far away in the overall knowledge graph, right? So to ensure that, we want to see the nature of connectivity of the graph given by the minimum of AQ and that permuted AC, right? So how connected is this subgraph? Now, elementary, computer science 101 algorithms course will tell you to find the largest connected component in this minimum or intersection graph, and then count nodes and find out what's the size of the largest component, right? But in fact, there are ways to do parallel computing, which gives you a way to do what we call a neural gossip. It's a fancy name. It basically says we initialize each node to a vector of all zeros and 1, 1 for its index position. Okay, and then these nodes start exchanging these bit vectors, and I keep on setting bits to on if my neighbor has it on. So at the end of it, B has set this bit for A has set that bit for B, and so on, right? So in this smaller component, each node gets a 2-bit set. In the larger component, each bit eventually gets 3-bit set if this gossiping happens for a number of steps which is proportional to the diameter of the graph. Okay. Now, we can just take the L1 norm of these vectors, and this will give me 3 for these 3 guys and 2 for these 2 guys. We take the max over all the nodes and we get the size of the largest connected components. Trivial stuff. So now the complication is that I was arguing all this for the case where AQ and AC were binary, and S was also from the space of hard permutation matrices. Once we relax them, the gossip leaks because there are non-zero elements everywhere, right? And now we have to do some very careful learnable thresholding to decide how far the gossip should go and how far it shouldn't go to approximate well the size of the largest connected component in the graph. Once we succeed at that though, we can tack on this continuous objective with the earlier objective of query graph coverage, and now the joint optimization will give me good embeddings of the query graph into the corpus graph, which are also encouraged to be connected because it has to have a large connected component. Okay. So I will not describe tables of numbers because we got some results, but I wanted to just present some ways to design neural algorithms which are transparent and not go by the conventional wisdom of throwing our problems under existing networks, because those are first of all not transparent, they don't explain what they do, they might take more training data. We are asserting some inductive bias through the structure of the network and therefore solving our problems more efficiently. Lastly, I'll bring in the issue of node and edge features as was asked in a question. So a real knowledge graph, for example Wikidata, has nodes which are entities and edges which are relations with given types. And these graphs have like tens of millions or even billions of nodes and hundreds of billions of relation edges. But that's true only of English. If you look at, say, Indian languages, their corresponding knowledge graphs are very small and impoverished. And one big question is our techniques for merging graphs into each other, can we reuse them for aligning, say, the English knowledge graph with the Telugu knowledge graph, by which information can flow both ways and enrich both the graphs. Okay. Now, people have tried to look at that resulting knowledge graph as a tensor, a 3-axis tensor, entity times relation times entity. So subject, relation, and object, and then try to factorize it in various ways. I don't have time to go into the details. Various kinds of factorizations are known. Among the simplest and fastest to compute is what's called the distmult embedding, where every entity and every relation becomes a single dimensional vector, and the raw score in our belief in the validity of a subject relation object triple is proportional to the inner product computed 3-way between those 3 vectors. So SD times RD times OD summed over all the Ds. Now this is symmetric in subject and object, so this cannot even model asymmetric relations or antisymmetric relations like X is parent of Y. The score of X is parent of Y and Y is parent of X will be the same in this story. So that's unacceptable, and this was fixed in a model where each entity and relation become a complex number, and then the score was extended to be the real part of the subject and relation and the object conjugate in a dot product, in a 3-way dot product. And this lets us nicely model symmetric, asymmetric, and antisymmetric relations. So those things work really well, but we'd also like to now align multiple knowledge graphs. For example, we have the English knowledge graph and the Russian knowledge graph. And I'd like to predict if the Russian relationship Stolitsa, hopefully I'm pronouncing that right, is the same relation as capital of in English, like city, capital of state. Now, if Tokyo, which is Tokyo here in Russian, and Japan, Japan in Russian, are related by the capital of relation and also by the Stolitsa relation, that gives you enough strong hint that those are actually the two same relation. But we can also extend it from soft evidence like this. So now we have this dual behavior. If two entities have the same connected colors to the similar connected objects, then they are likely to be the same entities. Conversely, two relations are likely to be the same if they connect similar subjects and objects. So it's like a chicken and egg, right? So similar relations connect similar entities and so on. So we have designed networks which solve the earlier tensor completion problems jointly with these two new tasks of inferring entity and relation equivalence, and this actually benefits all the tasks. So each task actually benefits the others. So in conclusion, I have presented just very small vignettes of the design of neural architectures for good typical case performance for difficult classical graph problems, and these are motivated by multimodal search applications. We are starting from text and images, but we hope to get someday to other real applications in science. And our goal is to have very distant supervision, as little human labor as possible. And I've given three flavors here. The query graph edges have to be a subset of the corpus graph edges, but then the corpus subgraph has to be well connected. And finally, is alignment and completion complementary to each other? Okay. So thanks for your attention. I'm happy to take questions. Yes.
Thanks for the talk. Sorry, this is amazing. Yeah, sorry. So the choice of S, is it just analytical advantage, or there's some physical interpretation as well? The double stochastic matrices. This time I'll be
So we
careful.
start with the permutation matrix, which says
Yes, I know that.
node here maps to one node there.
Yes, and then
right. So that's a nice question. So there is an optimization angle to this. So if you suppose you take, I wish I had a board, but suppose you have a vector of numbers a1 through an, and you want to do something as trivial as find the maximum of that, right? So you can write this as a fancy program. Says find a z which is over the unit simplex such that a dot z is maximized.
a simplex algorithm.
Right. So now you pile on all the mass of z into the largest position a max, and that would maximize a dot z.
Right.
Now that's max, but now if you add the entropy of z, so now you're saying I want to maximize a dot z, but I want to smooth out the entropy of z a little bit. It can't be so spiked.
Right.
That naturally gives you softmax through dualization. So just like max smooths out to softmax, you can show that a permutation, a hard permutation, softens out to a stochastic matrix under entropy requirements. Not only that, it gives you an efficient iterative optimization, so you don't have to actually solve an LP.
I see.
Thank you for your presentation. I have a quick question. If I have excellent information about the weights of edges and nodes, will it help in discriminating and identifying properly?
Great question. I didn't have time to get into that. It's not only a matter of weights on the edges, but the edges are expected to have rich features on them.
Okay.
For example, all the kinds of relations in a knowledge graph, like born in, citizen of, captain of cricket team, works in an organization, each of them is a different type with lots of features. I am scared to speculate on chemistry because I know nothing about it, but I imagine that a bond has many properties like energy.
It is important in chemistry because you just have carbon-carbon bond.
Yes.
It could be a double bond, it could be a single bond.
Exactly. So that's definitely something our model can extend to, and we are interested in looking at that.
Okay. Thank you.
Yeah, hi. You talked about matching these graphs up, but you also mentioned that some of the graphs can have like a very large number of nodes and so on. So can there be ambiguity when you produce these graphs from images in the first place? And how do you deal with that?
Absolutely. There can be ambiguities. There are also immense scaling challenges that I can talk to you about offline.
Okay.
We are thinking of graphs, the larger graphs, either there are a large number of them and they are modest in size, like graphs extracted from pictures, or there is one giant knowledge graph with billions of nodes, and here is a query graph with 5 or 10 nodes. And I want to hunt out where, among those 5 billion nodes, which tiny subgraph looks closest to it. And there are enormous indexing challenges that we are also trying to look at.
I think if there's no question from the students, we'll move on to the next talk. Sorry, but I think all of you know we are probably going to hear a lot more on this area in the afternoon session on
Oh,
Chat
yes.
GPT and on multi-language
In my longer
models,
version, I actually
etc.
had a slide saying, oh, but LLMs can do all of this anyways.
Yeah. Okay. Yeah.